we'll be looking at electrochemistry and thermodynamics in this CHEM 1820 course. This is lecture 1, so we want to start out with basically some foundation knowledge. Alright, one of the best textbooks that you could use is Elements of Physical Chemistry by Peter Atkins and Julia De Paula. This is a nice little textbook that should be helpful in developing your understanding of the basics of thermodynamics and electrochemistry. Okay, so let's see if we can get started. Now, what is thermodynamics? Now, thermodynamics is a study of the transformation of energy into its various forms. And now, energy can be defined as the capacity to do work or to transfer heat. All right, and this is a simple definition that we're going with for energy. In chemical thermodynamics, though, we are interested in the transformation of energy in chemical systems. That's what we are interested in. So let's say, for example, we're looking at something like octane burning to give us carbon dioxide and steam. Now, when you do that, some heat energy is also released. Now, heat energy is detected as an increase in temperature, right, or a temperature difference. So, of course, if you should touch a cup of hot water or tea, then what you'll feel that the cup is warm. Why? Because the temperature of the cup is above that of your body temperature. So, temperature or heat is detected as a difference between your body and the equipment or the item in question. Now, for this reaction, that is the burning of octane, there will also be a rush of wind or hot gases coming from this reaction due to the production of a significant amount of carbon dioxide and also water vapor. Now, I can tell you straight up that this is the part of the reaction that will do work, whereas the heat, of course, is the heat represented by Q. Now, you'll see what I'm talking about when it comes to Q and W shortly. Now, let's consider two other reactions in building up our understanding. So the same octane reaction, of course, we said that heat will be produced, yes, and also work will be done. The work is done by the gases, and of course, heat is the heat. Now, where did this heat energy come from? Was it created during the reaction? And that's a question. Look at this other reaction, right? We have hydrated barium hydroxide reacting with ammonium nitrate. And in that process, heat is absorbed, right? So on the reactant side, there is heat. But on the product side, we don't have heat. We have work, but we don't have heat. Where did this heat energy go? Was it destroyed? Now, the law of conservation of energy states clearly that energy cannot be created or destroyed, but it can change from one form to another. Right? And this is important. So energy is conserved. Okay, the total energy is conserved. It can change from one form to another, but the total energy is constant. Now, in chemical systems, energy is stored internally as potential and kinetic energy. What do I mean by this statement here? This statement is basically telling you that in a system, let's say this is our system, all right? The energy in that system, the total energy is equal to the sum of the kinetic and the potential energy. In other words, the energy within a system can be divided into kinetic and potential energies, right? So these are the two broad categories of energy that exist within a system. Now, for kinetic energy, the kinetic energy in the system can be decomposed or separated rather into its constituent forms translational energy, rotational energy, vibrational energy, and electronic energy. Okay? So even the kinetic energy has some, what we say now, some subgroups, some subcategories. All right, and these are the subcategories. Okay? There's also potential energy in the system as mentioned earlier. Now, the potential energy in chemical systems is generally stored in chemical bonds. All right? Potential energy is basically energy which exists by virtue of the position of a body. Whereas kinetic energy is basically energy of motion. That's what it is. It's energy of motion. Okay? I would say that the total internal energy or the total energy in a system is equal to the sum of the kinetic and the potential energies. Now, let's move on further. And we want to, as we move on, to mention the first law of thermodynamics. And it states, and I will read from here, when a chemical reaction occurs in a closed system, the change in energy of the system must appear as either heat or work, Q or W. Alright? So they're saying this. Change in internal energy, and U means, is used to symbolize internal energy. So the change delta, change in internal energy, is equal to heat or work. Alright? Look at what it says. When a chemical reaction occurs in a closed system, and this is important, closed system, the change in energy of the system must appear as either heat or work. Now we'll say some more stuff about that shortly. Now, this statement is a statement of the first law of thermodynamics. Right? And note, it only works for closed systems. Right? Now, what is a closed system? A closed system is one which is able to exchange energy with its surroundings but not matter. Okay? So the mass of the system is constant. It can exchange energy with its surroundings by exchanging in the form of heat or work. So let's say this is the system. Energy can go out, it can also come in. So this is energy. All right? That energy must be in the form of Q or W. Okay? That's what it is about. Q or W. The energy exchange with its surroundings must be in the form of Q or W. But guess what? For this system, the number of particles in that system, which is the definition of mass, right? Remember mass. Mass is just the number of particles in a body. That's what mass is. So the mass of the system must remain constant. That is a closed system. It does not exchange matter with its surroundings, but it can exchange energy. Okay, so internal energy change, delta U, of course, you would imagine that when you're calculating a change, delta U, it must be U final minus U initial, which makes sense, of course. Okay, now with the first law of thermodynamics, delta U must be manifested as QRW, as mentioned earlier. Okay, but generally we know how we calculate a change. It is U final minus U initial. Okay, that's how we generally calculate a change. Now you'll see how we apply this further shortly. Now, how can we quantify things like heat and work? Because we keep mentioning heat, we keep mentioning work. How is it possible that we could quantify such a thing or such things? Now, work. What is work? Now, work is done when a body is moved some distance by a force in the direction of that force. All right? That is basically work. Okay? And so what you find is that work is calculated from force times distance. Now, note, force has units of newtons. And distance have units of meters. So if you're multiplying newtons by meters, then you'll end up with a value with units of Newton meter. Now, the unit of work is the joule. So what this is saying to us is that Newton meter is equivalent to joules. So 1 Newton meter is equivalent to 1 joule. Okay, so work is calculated from force times distance. Now you're probably wondering, how are we going to apply this type of thing to chemical systems? And you will see shortly. You'll see how this can be applied to chemical systems when we go to calculate work done by chemical systems. Now, so this is more like mechanical work. We can also calculate electrical work, and electrical work is done when a charge is moved against a potential. So electrical work is equal to E times W. E will be the voltage times the charge, which will be in coulombs. Okay? But of course, our main focus for this course will be mechanical work. Okay? Now, heat. How do we calculate heat? How do we calculate heat? Now, we can use any one of these two formula. We can use any one of these two. Q is equal to mc delta T, or Q is equal to C delta T. Now you're probably wondering, what is the difference? When do I use which one? Alright? Now let's look at the first case. Q is equal to mc delta T. Now notice that the C is in lowercase. Lowercase c is the symbol for specific heat capacity. Now, what is specific heat capacity? It is the energy required to increase the temperature of 1 unit mass of a substance by 1 unit temperature. Alright? So it's the heat required to increase the temperature of 1 unit mass of a substance by 1 unit of temperature. Okay, so that's why it's called specific. It's specific because it considers the mass of the substance. And that is why you have an M here, which specifies the mass. Okay, so the units for specific heat capacity will be something like joules per Kelvin, right? Per kilogram or per gram, right? Yes, because it specifies the mass. Now, a lot of times we are not dealing with specific heat capacity. A lot of times we are not dealing with that type of situation, and so we don't have the mass. But what we have is the temperature change. So we'll use this one. Q is equal to C delta T, and it just tells us the amount of heat. It's not specific. It's not per gram. Okay. So C is heat capacity, not specific heat capacity. Uppercase C, this one is heat capacity. Now, what is heat capacity? It's just the energy required. It is just the energy required to increase the temperature of a body, right, by 1 unit. It doesn't matter the size. It's just the energy required to increase the temperature of a body by 1 unit temperature. That's it. Right? So if you're talking about degrees Celsius or Kelvin, it's the energy required to increase the temperature by 1 degree Celsius or by 1 Kelvin. Okay? Okay. So most of the times you'll find that we'll be using that one. Okay? Right. And of course we know that delta T is just a change in temperature. Okay? So let's say you have a bucket of water like that. Let's not say it's water. Let's say it's just some liquid. Let's just say it's a liquid and we call that liquid A. If you are told that its heat capacity is something like 10 kilojoules per Kelvin, all right? And let's say somebody asks you what energy or what amount of heat would be required to increase the temperature of this bucket of water from 10 degrees Celsius all the way up to 25 degrees Celsius. All right? What amount of heat would be required? Now we have the heat capacity. Heat capacity, look at the units for it. It's kilojoules per Kelvin. It is the amount of energy required to increase the temperature by 1 Kelvin. So it says it takes Look at what it says. It says 10 kilojoules are required to increase the temperature by 1 Kelvin. Okay? Now, the first thing I would do, I realize that, okay, I don't have a mass, so I don't know how much water is there and how much of liquid A, I should say, is there. Then I say, okay, clearly, this is the formula. Q is equal to C delta T. Now, I know C, so I have C already. What is delta T? Well, I can just take the difference of these two, which would be 25 minus 10. Okay? 25 minus 10. And that looks to me to be something like 15 degrees Celsius. This is a temperature change. This is delta T. It's not T, it is delta T. Okay? Now, I'm going to do something and you're going to wonder what I am doing. So Q is equal to 10 kilojoules per Kelvin, right? Times the 15 degrees Celsius. Alright? And so you know, I can work that out easily. So 10 times 15 looks like about 150. Alright? Degrees Celsius and the Kelvin cancel. Of course, that is where you'll wonder, how can you cancel now degrees Celsius with Kelvin and they're not the same? Now, let me answer that question. What we are, this 15 is actually delta T. It is not T, right? So it's just it's a change in temperature, not temperature. It's a change in temperature. There's a difference. So you don't have to convert it to Kelvin. However, if you don't trust what I am saying, you could go ahead and convert the 25 to Kelvin and convert the 10 also to Kelvin. When you do the subtraction, I am telling you that you're going to come back down to 15. And so that is why I'm able to do that a while ago, which seems funny. Okay, so you can try that. Okay, so that was just a quick example. That's how we would calculate Q. Now, let's talk about some other stuff, resign convention and stuff like that. Remember that the internal energy change occurring in a system is designated by delta U. That is the symbol for internal energy change. U is the symbol for internal energy. Delta U is the symbol for internal energy change. Now, delta U is equal to U final minus U initial. Well, that is how you would calculate any form of change. Not just delta U, but any change at all. It's final minus initial. However, we know that for a closed system, delta U is equal to Q plus W, according to the first law of thermodynamics. Now, let's say a few more things. So, of course, there's a sign convention which must be followed to be consistent with the way we have designated delta U. Now, for instance, let's consider a case where work is 0. All right? Here's the formula. What if work is 0? So, if W is equal to 0, then clearly delta U is equal to just Q. Okay? That is what is going on here. Now, suppose heat energy leaves the system when the reaction occurs. Think about it. If heat energy leaves the system when the reaction occurs, then there will be a decrease in the internal energy. Think about it. If you have a cup of tea, and just after pouring the tea from the kettle, you touch the cup or the mug and you feel that it is warm. After about half an hour, 1 hour, the mug will be basically at room temperature, thereabout, or a little bit above room temperature. The point is, it would have lost a lot of heat. In other words, the internal energy of the mug would have decreased, all right, because of the loss of heat energy. Okay? Now, how can I prove such a thing? What am I talking about? Okay, let me show you how. Now, remember, we say that W is equal to 0. So, delta U is equal to Q, right? Okay. How do we calculate Q? Q is equal to C delta T. Okay, you don't know the mass of the liquid in the mug, so just use C delta T. All right. Let's say this is the mug. A matter of fact, let me draw it better than that so that you don't confuse it with U. My mug looks like a U. Alright, so let's see if I can do better. Alright, anyway, I'll just draw it like this. Alright, so this is the mug. Heat is continuously being lost. Okay, now after pouring the tea from the kettle, the temperature, let's say the temperature was like 50 degrees Celsius. 1 hour later, and the temperature is now, let's say, 25 degrees Celsius. I'll call this T1 and this one T2. Of course, T2 is less than T1 because the temperature would have decreased, all right, over time. So delta T would be T2 minus T1, which is basically T2 is T final, basically. Okay, T2 is T final. So it's T2 minus T1, which is the same thing as saying T final minus T initial. So it's 25 minus 50. This equals to 25 degrees Celsius. That's the temperature change. But this 25 is negative. Okay? Because you're taking away a bigger number from a small number. So you have minus 25 degrees Celsius as your temperature change. There's a decrease in the temperature. If the heat capacity of the liquid in the mug, which is your tea, is something like, I don't know, let's say 5, or let's say 2, let's use an easy number, let's say 2 kilojoules per degree Celsius or per Kelvin, all right? Then clearly you can see that when you say C times delta T, you'll end up with a negative number. Right? Because it would be minus 25 degrees Celsius times 2 kilojoules per degree Celsius. You will end up with Q being negative. In other words, delta U would be equal to some negative value. In this case, it will be 2 times minus 25 would be minus 50. Alright, it would be minus 50 kilojoules of heat would have been lost. And that is equal to a negative delta U. Now, if delta U is negative, what it is saying to us is that U final must have been less than U initial, such that when you say U final minus U initial, that's why you ended up with some negative value. All right, and that is what I am explaining here. Here it is. Here it is. That's what I am explaining here. Okay? Yes. So whenever a system whenever heat energy is lost from a system, its internal energy tends to decrease. Its internal energy will decrease if work is equal to 0. Now later on we'll consider what if work is done on the system or by the system. What happens to the internal energy even though it is losing heat? What if work is done on the system? What will happen to the internal energy? And we will look into that shortly. Okay. Now, for systems where heat energy is lost, we generally say, look, such a system is an exothermic system, or the process occurring in that system is exothermic. And we like to say net exothermic because the fact is, during chemical reactions, energy is both absorbed and released. However, if more energy is released than that which is absorbed, right, then the process is said to be net exothermic. And the opposite is also true. Now, here you go, some sign conventions you could look at. Okay. All right. Let's go to look at something now which is also quite important. The whole instrumentation, release of heat, absorption of heat energy, as we were mentioning just a while ago. Now, we have what we call constant pressure calorimetry as well as constant volume calorimetry. And these are just experimental setups that are used in measuring the heat released or absorbed by a chemical process. We have our constant pressure calorimetry, which can be done easily in the lab, just using something like a styrofoam cup or some sort of insulating vessel, a thermometer, and a stirring rod. Okay, so for such a system, you could calculate the heat released or absorbed easily. What you need, what you'll be measuring is the initial and final temperature. And if you know the mass of the liquid or mass of the reacting species and also the specific heat capacity of the combined reacting systems, then you could easily work out the heat absorbed or released. Okay, so let's say you're mixing 25 mils of something like HCl, and you're mixing another 25 mil with of sodium hydroxide with that HCl. All right, so that's a total of 50 mils. If you can work out the mass of the total mixture, then you already have your mass. If you know the heat capacity of the mixture, the specific heat capacity, I should say, then that's good. And then all you have to do is to measure the initial and final temperatures over time. And then you can calculate Q, the heat released or absorbed during that reaction under constant pressure systems or constant pressure conditions. Sorry. Right, so you could do that, and you could get the heat release or absorbed during the reaction of hydrochloric acid and sodium hydroxide. So constant pressure calorimetry, is quite a simple setup, and it does work because generally atmospheric pressure is constant throughout the day. It does not, it might change, but it does not fluctuate significantly throughout the day. You have also what we call constant volume calorimetry, and this makes use of what we call a bomb calorimeter. So you use a bomb calorimeter to basically convert your foods to or your sample to its constituent elements, um, and all its energy will be released, but in the form of heat only. And that heat energy will be used to warm a water jacket, which is outside a container that we call the bomb. It's a thick steel vessel, and you collect the temperature, and so you can easily work out the amount of heat um, released. Now here's a very important reaction that we all make use of in preparing our meals. The burning of propane in our propane tanks at home is known to release something like 2,220 kilojoules per mole of propane. And that's a very important reaction because, like I said, this is the reaction that we use to heat our pots such that we can prepare our meals. Now, what we want to look at now is how can we quantify mechanical work done by chemical systems? How can we quantify mechanical work? Now, earlier I mentioned that work is equal to force times distance. Okay? Well, so work is equal to force times distance. Now, how can this be applied for chemical systems? Now, look at this diagram over here to our right. Let's say you have in a cylinder a chemical reaction occurring, and we call that chemical reaction system. Okay? Here we have a movable piston, meaning that this piston can be pushed upwards or downwards. Okay? This arrow pointing down on the piston is atmospheric pressure. That's the pressure caused by the weight of the molecules in the atmosphere. That's atmospheric pressure pushing down on the piston. So in our system, which is that's our reaction, our reaction could occur, and if it occurs and produce gas molecules, if in reacting it produces gas molecules, those gas molecules requires more space and could push the piston upward. So we end up with the final state. So this is the initial state. Look at the final state. Now the piston traveled some distance upward, pushing back against the atmosphere. Remember, work is force. So those gas molecules must have exerted some sort of force to cause the piston to travel some distance. And so we can calculate the work. Now think about it. If this is a cylindrical vessel, if the piston was moved backwards by some distance, what essentially took place is that the volume of the cylinder would have increased. All right? Yes, the volume of the cylinder would have increased. So look at the volume. And look at it now over here. You see? The volume would have increased. So there's a change in volume as a result of this change in height of the cylinder. Okay? Now this change in height, as you can see over here, we tend to refer to it as d, distance. Now, let's look at calculating using all of this information to calculate the work or to come up with some measure or estimation of the work. Now, first of all, pressure is equal to force over area. All right? So external pressure, EXTS, is equal to force over area. So if we rearrange this formula a little bit, we can get that the force is equal to pressure external times area. Okay? Yeah, so we just rearrange this formula by saying P is equal to F over A. So we multiply by A cancels A. So force then is equal to P times A. Okay? All right, here it is. Now, so we have force. We have an expression for force. What we will do is to take this expression and we could put it right here. Okay? So what we find now is that work is equal to P external times A. Alright? This is the force, don't forget. Times D, which is the distance. Okay? Now, remember, distance is equal to the change in height. Okay? As given here. Now, remember how to calculate. Remember how to calculate the volume of an object. It is the cross-sectional area of the object times its length. Most of the times we just say area times length, which is distance. Any form of change, any change in the volume must come then as a result of either a change in the cross-sectional area or a change in the distance. In our case, what we have is a change in the distance. We have a change in the height, which we refer to as the distance. Okay? So from this, we can do a little rearrangement, and we get delta H is equal to delta V over A. This delta H, remember we say it's the same thing as D. Okay? Now, all we have to do is to take up this part. Okay? And substitute it here, because we say that delta H is the same thing as D. Substitute it there. Once you do that, this is what you will have. You will have work is equal to P external EXT times A, now times delta V over A. A will cancel A, so look at what you have remaining. This is what you have remaining. Work is equal to P external times delta V. Therefore, the work done by the system, if we say work is done by the system, we can put a negative sign. So the negative sign is not something that you figured out or you derive. It's a convention that we have attached at the end of the derivation, just to say that work was done by the system. Now, if we are wrong in applying this formula and work is actually done, our work was actually done on the system, then the sign will correct itself. You don't have to worry about it. So the work done by the system is equal to minus P delta V. Here it is. Okay? Now, just to mention a quick application of all of this. This is how your internal combustion engines work. All right? You have these cylinders. You have these cylinders, and inside these cylinders, you have a mixture of your gasoline and your air, and then you have gasoline and air mixed, and it's under high pressure. Because it's under such high pressure, it's explosive. And so once you put a spark to it, there will be an explosion. Once you have an explosion inside any of these, the pistons will be pushed down. And that motion, up-down motion, you remember, if you look here, you'll realize that some pistons are up while some are down. So they are arranged in such a way that when some are up, some are down. And this up-down motion is translated into a circular motion by the crankshaft. Right? And so your wheels now, will be turning. So this work, right, which is turning of your car wheels, is actually done by gases due to an explosion inside your um, engine's cylinders. Okay, so you can always check that out. That's just FYI. Right, so let us consider the reaction we discussed on slide 2, or discussed earlier. Look at this reaction. What we have is propane gas reacting with oxygen gas to give you carbon dioxide gas and water, right? It's liquid. The work done by this system is given by minus P delta V, right? Of course, you could calculate the volumes of all of these gases if you assume that they behave like perfect gases, okay? You could calculate the work, you calculate the volumes easily using the ideal gas equation. But we don't have to put ourselves through that. There's an easier way. We'll use the same ideal gas equation. Look at the ideal gas equation. It says PV is equal to nRT. Okay? If we look at a change in volume, then we have P delta V, alright, and this part should look familiar now, is equal to something also needs to change over here. If the temperature is fixed and R is fixed, then it could be delta N RT. If we're looking at work done, then we need to put a minus sign. You see? So what we are saying is that minus P delta V is also equal to minus delta N RT. So instead of using this part, we could actually use that. Okay? Now, you probably ask now, okay, we know R, universal gas constant. We know the temperature, right? The temperature would have to be given to us in the question or so. But what is this delta N? Delta N is the number of moles of gaseous products. Gaseous products, remember, gaseous products. If there's a liquid, you don't consider it. Minus number of moles of gaseous reactants. So for example, if we consider this reaction, delta N would be, let's look at the gaseous products. Well, this is a liquid, so we don't consider that. Gaseous product is carbon dioxide, and it's 3 moles of carbon dioxide. Right? This is delta N that we are calculating, minus 5 moles of oxygen, which is a gas, and 1 mole of propane, which is a gas. 5 plus 1 is 6. So 6. So we end up now with minus 3. Let's actually do the calculation. So here it is. We're using work is equal to minus delta nRT. Work is equal to, remember there's a negative sign naturally on the formula, so we put that back. 3 minus 6, which is the 3 moles of gaseous product. The water is not considered because it's a liquid. Minus 6 moles of gaseous reactant. Times R, right? Times T, right? 25 degrees Celsius. Here is the energy. And the energy, the work is positive. What does that tell you? What conclusion or conclusions can be drawn from that? The fact that the work is positive indicates that work was done on the system and not by the system. In other words, the system was compressed. What am I talking about? Look at what happened. The reaction is occurring in this vessel. All right? We started out with 6 particles of gas. It's 6 moles, but I'm just calling it 6 particles of gas. At the end of the day, we ended up with how many particles of gas? Just 3. Right? It's 3 moles, but I'm just calling particles. Which direction you will have some liquid, but the volume of a liquid is very small compared to the volume of a gas. So the liquid will not affect the volume, right? Which direction you think the piston will move in? Of course, the piston will move down because you have a small amount of gas molecules now, so the piston moves down. So this is compression. All right, this is compression. Work was done on the system and not by the system. If work is done by the system, then you need expansion. In other words, the piston needs to move upwards. The fact that the piston moved down indicates that work was done on the system. Okay? Yes, and that is why the work is positive, because work was done on the system and not by the system. And if you think about it, if you have a balloon, and you started out with a certain amount of gas molecules in the balloon. Huh? So the balloon is large and stiff. If you release some of the gas molecules from the balloon, of course, you expect that the balloon will become a little bit smaller and it will be a little bit soft. This is the situation where you release some of the air from the balloon. Right? You release some of the air particles or the air molecules, so the balloon becomes soft. Right? Work was done on the balloon and not by the balloon. You see, it's compression. And so the work for this is positive. Okay? Now, we'll talk more about work and, just basically look at some knots of work and heat in our next discussion. I'll probably do a summary video of heat and work in chemical systems. But that is that. Thank you for listening.